Today we will discuss 420 milliampere current transmitter, which is used extensively in analog domain, and then we see how to design the 420 milliampere current transmitters for various transducers, and then we also discuss how to do error budgeting for the current transmitters. So, this is basically called 4 to 20 milliampere current transmitters. Overall it looks like this, that normally what is done is that you have a supply like 24 volt supply normally used in the industry, then they run two long wires like this. Typically this is in the control room, and this is at the site. You have this 420 milliampere current transmitter. This is 4 to 20 milliampere current transmitter. Then this is having connected to a transducer. Say for example, in this case potentiometer is the transducer. Potentiometer is the transducer. So what is actually done is, this potentiometer, this is attached to mechanical system. So essentially what happens when mechanical system moves, the potentiometer center point actually moves. Now what is required is the mechanical system's position to be transmitted as a current. For example, when mechanical system is at one end, mechanical system at one end, then current will be 4 milliampere, and at the other end of the mechanical system, current should be 20 milliampere. So in the middle, suppose the potentiometer in the middle, that is the mechanical system is in the middle, then the current will be 12 milliampere. So obviously what it basically varies linearly. In the, if you look at like this, that is at 0% when the mechanism at 0%, current will be 4 milliampere. At 25% of the movement of the mechanical system, it will be 8 milliampere. At 50% it will be 12 milliampere. 75% it will be 16 milliampere. 100% it will be 20 milliampere. That is how normally it transmits. Now if you look at this, this is getting power only from these two wires, because this does not have any power supply by itself. So whatever power that is required for the operation of the electronics that is there inside, that is actually derived from this wire only. And then the signal, the signal is here, the position of this potentiometer. When the position varies, the resistance value, the voltage across these 2 points for example varies. Normally this is connected to a fixed voltage. So voltage across this varies. According to the voltage, the current in this will be varied. Like this, at 0% it will be 4 milliampere and so on. It is adjusted like that. Now this is a very classical system, and it is used extensively even today. Now this card advantage, this is called two-wire system, because the only two wires are used to carry the power, and the same two wires are used to carry the signal. Now actually what they do is, in actual use, to know the signal position, they connect one resistance here and they measure the voltage across this. Voltage across this gives you the position information. If for example, if it is a 100 ohm resistance, they normally connect up to 600 ohms. 100 ohm resistance, and if there is a 4 milliampere current through this, for example the 4 milliampere current through this, then you will get 0.4 volt, indicating it is at 0%. If it is 12 milliampere through this, then it will be 1.2 volt, indicating this will be 1.2 volt, indicating that the mechanical system is at 50% level, halfway through. Like that normally it is done. Now, why this system is very popular and then why it is still used, what is the basic reason for this? Actually, this system is used mainly because this is not prone for noise, because for example, if I take the system, because normally this will be in the control room, in a process control industry, this will be in a control room, and this is actually this mechanical system will be in the field, maybe the distance between these two can be up to 1 kilometer. Now, what happens, you see that this wire is actually routed for a kilometer long. There are two problems associated with that. Normally, of course, they put a resistance here and to know the current that is flowing through that, which is acting as a signal. Now, if you see this loop, let us say enormous amount of loop area, if you take this loop area. Now, we know that there is a change in magnetic field in this loop, there will be induced voltage in this loop, noise induced voltage. So, the change in magnetic field in this loop will induce a voltage like this, that actually should not influence this signal. That is the aim. For example, instead of having a current signal like this, if it had been a voltage output, like for example, if I send a voltage output, then what happens, you have this, then I have a system like this, potentiometer is connected to this, then I send a voltage output to the back, and I put a resistance here and measure. This is a voltage output. If it is a voltage output like this, the problem is that you see there is enormous amount of loop here in this area. So, this will be sending some voltage and that is supposed to get here. Suppose if this is sends 1 volt and you expect to get 1 volt, leave alone the loss that is taking place on the wire and so on, but the voltage induced in this loop due to changing magnetic field externally, there is a magnetic field and that there is a changing magnetic field, then you will have a induced voltage in this. This induced voltage will appear along with this. So, this is sending 1 volt here, this is sending 1 volt, but whereas you will get 1 volt plus this noise is what that you expected to get, and that sometimes this noise will be much higher than this signal if you are considering 1 kilometer long wire, wherein other wires are carrying current and they all will produce a magnetic field, and you will have enormous noise voltage induced. So, if you use a voltage transmitter system, then this is prone for noise, whereas if we go back to our system, that is a current transmitter, if you go back our current transmitter, that is in this case what happens if there is a noise voltage induced in this, that will induce a voltage in this, but this voltage will have no influence on the current of this, because this current transmitter make sure that only the current that is required 4 milliampere alone will be flowing, and this current depends only on this position of this, not depends on the what is voltage across what it is receives, because voltage across this can change either because of this change or because of the resistance change or because of the induced voltage change. All these things for all these things this current transmitter is not going to respond. It will make sure the current is always constant, and that depends only upon the potentiometer value. So, if I use 420 milliampere current transmitter, or for that matter any current transmitter, that it is not for not noise prone. That is one of the biggest advantage other than other advantages that you get, because it has only 2 wires and so on, but more than that the pickup issue is greatly reduced because of this current transmitter. That is why these 420 milliampere current transmitters are used even today in the industry, and there is no alternate for this really from the noise point of view. Okay. So, this is the background of this 420 milliampere current transmitter. Let us see how to design the system, because as I said, this current transmitter what we are designing here should send a current through this, that is the same current comes and same current goes here, and that current should be independent of whatever the voltage across this, that is within the limit, and then it also should be independent of the noise induced voltage, and that should vary with this. And then this unit minimum current is 4 milliampere, we said it is a 420 milliampere system. So, when its system is at the lowest, the current in this will be 4 milliampere. So, obviously this should not consume more current, this should not consume more than 4 milliampere, and even whatever current it consumes, that should be constant against temperature and other parameter variations. So, that the current will not change for other variations, only this variation should change the current in this. So, we will make sure that we design a system such that this takes only less current, and the voltage across this changes will not have any effect on the current that is flowing. So, considering that, let us see how to design the system. Normally, if you see the expected variation, this supply variation we said normally 24 volt, but very often it varies from 18 to 36 volt in the industry. So, this variation also should be taken care, plus the noise pickup also should not create any problem. So, if I make a system, then what I have to do is I have to make a voltage regulator first, and then voltage regulator should regulated voltage should be used to make a current source. So, that current in the loop varies depending upon the position of the potentiometer, because in this example we have taken potentiometer as a transducer here or position. So, I take this, then how will I make a voltage regulator? For example, if we take our classical voltage regulator, one possibility is I can have this. So, I can have a regulator. So, I put on Darlington here, then I have to put on Darlington, so that this base current is very small. Then if my output voltage is regulator is this, then I have to divide the regulator voltage, output voltage, then I feed this to the error amplifier. So, error amplifier is connected here, then this is supposed to be connected to a reference voltage, I connect a reference. So, it is a simple voltage regulator, but there is a small change. What I do is then there are various ways of obtaining this. I put on Zener here, connect to this, then I connect on resistance here, this I connect to this. Now, this is the voltage regulator that works, and supply for this I connect this to ground, and the supply plus input I connect to the output. Connect to the output. This is the typical voltage regulator used in the 4 to 20 milliampere current transmitter. This voltage regulator's output, that is the output of this will be fed to a current transmitter. I will show you this. What we do is in actual case we will put a current transmitter here, that will be powered by this regulated voltage. Then we will have our potentiometer connected here. When the position varies, the current drawn by this varies, and so does the current that is coming from here. So, the total current that is going will be the current consumed by this and the current consumed by this plus the current driven due to this. So, we have first voltage regulator part, then we have the current transmitter part. So, first let us concentrate on the voltage regulator part, then we come to this current transmitter part. Now, if you take the voltage regulator part, this is the this is the reference voltage, and the output is actually divided by the voltage divider, and the fraction of the output voltage is given to the minus supply. Now, for example, if I the one important difference is the supply for this op amp is coming from the output. So, the supply is coming from the output. Now, if I, for example, we want 8 volt output voltage, electric voltage of 8 volt. If I want 8 volt here, I know that I have to get 8.6 at this point, because the base entry is 0.6. Then this has to be 9.2 volt. This has to be 9.2. If the base is to be 9.2, for example, in normal case we do not use this zener. So, we do not remove, I remove this zener. So, in the normal case we do not put this zener. So, if I do not put the zener, for example, directly connect, then if I want a 9.2 here, and if this is if the supply voltage for the op amp is only 8, then there is no way you can get 9.2 here, because the output will be less than the supply only. So, obviously to get 8 volt we need 9.2 here, and that is not for that, means this regulator will not work. To solve that problem only, we here put this Zener diode here. Now, the Zener diode is kept here. Now, and then we have a small resistance, is a very high value, in the sense that resistance will be very high value, that is kind of between this and this. So, what happens is, initially even if there is a current flows like this, then there will be small voltage drop across this. So, essentially this will not go to 0, and then if there is small current through this, voltage at this point will be output voltage plus whatever voltage drop across there in the Zener. It may not be full breakdown voltage of the Zener, but nevertheless some voltage drop is there. So, voltage at this point is output voltage plus voltage across the Zener. That means we can get voltage at this point higher than the op amp output by adding this Zener. That is the trick that we have done in this case to get regulated 8 volt output 8 volt, and then we regulated voltage also 8 volt, supply voltage with op amp also we could operate at 8 volt. That extra boost that is required is coming from this Zener. This is a very important thing. So, essentially the Zener voltage provides extra voltage, that is say we call this is A. So, voltage at A is equal to op amp output plus voltage across the Zener. But voltage across the Zener need not be breakdown voltage. Zener is not equal to breakdown of the Zener, breakdown voltage, breakdown some voltage required, that is all, to make the system to start. So, that is why we have done it, we have added this Zener. But we may ask, why did you take this op amp supply? For example, you may ask, why did you take the op amp supply from here? You op amp supply, you may say you connect it to the input. For example, you may connect the op amp supply to the input instead of here. You can also connect like this. You can connect like this. Now, if I do like this, then obviously what happens? You that is, I will connect the op amp supply here. Then the supply of the op amp is much higher than what is required here, because this is around 18 volt or so, and getting 8 volt it is not a problem, and then you can remove this, directly connect, and even this is not required. So, it will work in the normal way. But then if you do this, when the supply voltage changes here, when when the supply voltage changes here, then the current consumed by the whole circuit should not change. The current flowing in this line should only vary because of this. So, that is why we are not connecting the supply for the op amp here. So, we connect the regulated output, because the regulated voltage always constant irrespective of what is there at the input. So, the current consumed with op amp also will be constant. That is why we are connecting this instead of connecting it there, we connect it here. But once you connect this, we need extra boost that is given by the Zener. That is why this configuration is used for this voltage regulator. Because of this, the current consumed by this is constant, because the voltage at this point is constant. So, current consumed by this is constant. Since this voltage is constant, current consumed by this also constant. These two resistors are constant. So, current consumed by this also constant, and we keep this one very large value 470K 1 mech like that, because we need only 20 milliampere here. So, obviously this base current is very small. So, this current very small current is enough. So, we will have a large resistance here, that is that makes that even if this voltage changes, the current change here is very small, and that will not affect the system performance very much. That is why we put here high resistance like 470K, and then make this regulator. The working of the regulator is straightforward, like our simple regulator which we have discussed. For example, if you want to keep at 8, I put this one, say 5 volts Zener here, 5 volts Zener here. Then I know that I need say 1 milliampere current through this. So, I need about 3K, I can put 2.7K resistance here, 2.7K. Then if it is 5 volt, I want say if I put here 100K, because we want current through this to be very small. So, I put 100K. Then this voltage across this will be 5 volt. Then if I want 8 volt, then I can select this one R2, such that you get 8 volt. That formula is very simple, because voltage across 100K is 5. So, that I can calculate. Voltage across 100K is equal to 5 volt. So, output voltage 5 volt divided by 100K into 100K plus X. So, that is supposed to be equal to 8 volt. So, the X can be determined, the value of the X can be calculated. So, you get the, so by you can get any voltage you want. In this case, we set this one to 8 volt. We set R2 for 8 volt, set R2 for 8 volt using the formula that I had discussed. So, if this is always sitting at 5, so in case if the output goes more than 8, then this point will go more than 5. Then if this goes more than 5, then this voltage will come down, because minus going up. So, this will come down. If this comes down, this will also come down, and so does this also will come down. So, in case if it goes below 8, then this point will go below 5 volt. Since this is lower than 5 and this is 5, output will go high, then this also will go high, and output also will increase. So, essentially if I am keeping this at 5, this also comes at 5, and that is how the regulation is done, and the circuit regulates and provides us with the 5 volt. And then we know that to avoid oscillation, we had to connect the capacitor here. That a small capacitor can be connected across this, so that no oscillation comes in. So, normally we put on capacitor here, but here we can't put electrolytic capacitor, because this is a 420 milliampere system, and if the electrolytic capacitor after some time if it leaks, then the current drawn by this will upset the other current in the unit, that will create a problem. So, normally we put small value 1 mF, 5 mF like that, not very high value to avoid oscillations. So, this is the voltage regulator part of this current transmitter. Now, we can go ahead and see how to design the next part, that is this current transmitter part, because the current that is flowing here returns here and that comes here, because in the actual use they will be using the on resistance here and measure the current, and that current should give the position information corresponding to this potentiometer. So, we have to design now, since the voltage across this is now constant, this receives a constant voltage. Now this current transmitter can be designed easily. Let us see how to design this current transmitter. So, design of a current transmitter. So, now let us start using the circuit like this. For example, I have this regulated voltage which was coming from the regulator, say that is 0, this is 8 volt. What I do is I have to connect the potentiometer now. So, I have this, I have this. If you want, you can retain this circuit also this side, that is your here is the Zener diode, connect this reference and then biasing the Zener this. Now, here we put the current, now this is the regulator part, and then we also said we put on capacitor here. Now, I put the current transfer, for that I take one operation amplifier. Then what I do is I will also connect on transistor here. Now, I had put the potentiometer. Now, what I do is I put the, this is the potentiometer. This, when the mechanical system moves, this the center tap of the potentiometer actually moves. So, when the mechanical system at one end, the potentiometer will be here at this end, making contact here. When the mechanical system at the other end, then the wiper moves and makes the contact at this point. So, if it is halfway, then potentiometer will be the center point will be at halfway point of this potentiometer. Normally, for example, they use this 5K part actually. So, essentially what is happening is when the mechanical system moves, the voltage across this, there is center tap to this ground, with respect to ground, if we take that voltage actually varies. Now, invariably, for example, this supply for this also can be obtained normally from the same this thing, whether it is regulated voltage, supply for this also can be from the same. Invariably, normally what is done is you can have system where this and this, for example, 4 op amps are there in one single chip. So, that if you give a supply to this one, the automatically other one comes, and you also need not look for the second op amp, the same package 4 op amps are there, one the second one can be used for this purpose. So, in a simpler system like this, you can take the op amp. Now, this and then we are design now, if this voltage varies, current through this should vary linearly. If this is at one end, we have to make sure the current, total current that is flowing here, all this current put together plus this current all put together should be 4 milliampere. When the potentiometer moves to the other end, that is at this point, then all this current plus current flowing here should make it up to 20 milliampere. That is what we have to do, and then the exact circuit design to be carried out for that. So, what we can do is we can connect that increase in this should increase the voltage here. So, obviously, we have to connect this this output of the potentiometer to plus terminal, so that when this increases, output increases. But then we also want to make sure that the current does not go very high. So, we give the feedback here, we put this, connect to this. Now, this voltage, whatever current that is flowing, develops a voltage across this, If more current flows, you will get more voltage, then you will also get more voltage. If the voltage more, this voltage will come down, and then this current also will come down. Essentially our idea is whatever voltage is there here, the same voltage will come here. So if I give more voltage, then I will get more voltage here, and then I also have to get more voltage, that automatically more current will flow. So if I increase this, then I will find that current is through this also increasing. Now only one small problem in this is that we have to make sure that when this at one end, for example if it is at one end, we will get 4 milliampere, but already you have around 3 milliampere current is flowing, here some current, here some current, and then the op amp takes some current, with all that some 3 milliampere flowing. So when potentiometer is at one end here, then you need a balance of 1 milliampere current, because if already 3 milliampere is going, then to make it 4 I have to send only 1 milliampere current. Then when it is at the other end, the current has to go to 17 milliampere, because already 3 is there, the current through this has to become 17, then it will go to the other end. But we know that if we are operating the operational amplifier in a single supply. If you are operating in a single supply, then there is a limitation that input of the op amp should not go below a certain level, and if it goes below a certain level, then the op amp will not work. For example, if we take 741, if I operate in a single supply, then I need minimum of 2 volt at the input, that means this should be kept at 2 volt. And similarly the top should not go very high, then if the supply is 8 volt, this should be better limited to 7 volt. So if it is 2 volt, this will be this end will be normally 7 volt. So only you get 1:3 variation in voltage, but current variation required would be around 1 milliampere to 17 milliampere. That is when the input is around 2 volt, you need 1 milliampere current. When the input is around 5 volt, we need current of 17 milliampere. That is roughly 2.5 time variation voltage at vary the current 1:17. That means it becomes a non-linear variation, and that is not acceptable. It has to vary linearly with the position here. So to tackle that issue, we can do a simple change. What you do is, I take this voltage, put on resistance, connect this here. By connecting like this, that problem is solved. Like for example, I take this one as R1, this R2. This is the main resistor, it is R. So by suitably selecting R, that is this resistance, then R2, R1, we can make it such that when the potentiometer is at this point, it is current, total current is 4 milliampere, the potentiometer at the other end, total current is 20 milliampere. Now how to select this R1 and R2, because assume that I will mark the points now. For example, I assume this is A, this is B, this point is C, and then this junction is T, and this is E, this point is E. So let us mark these points. Now for example, when the center tap is at A, then the potentiometer is the mechanical system it is at A. We need this op amp work, assume that we need 2 volt. Then I have to select this resistance is known, so I can select this resistance, say I will take this is R3, R4. So R3 and R4 I can select R3, R4 and this 5K pot. All these 3 can be selected such a way, voltage at A is 2. So what you do is select R4, R3 and pot such that voltage at A is equal to 2 volt. That can be done by varying the value of R4 or R3, and make sure that this resistance value is not very small, because the resistance value is very small, then large current will flow, and that itself will take, if it takes more than 4 milliampere, then the whole purpose will be lost. We can keep about 0.5 milliampere to 1 milliampere current for this, that is practical value, but we can adjust this to R4, because we know this is 8 volt, So, it is not difficult to calculate what is the value required for R4, because this is known as 5K. So, if the one can select R4, but normally we also have to consider if this voltage variation is say if this is 2 volt, and if I keep this one at 4 volt, for example I can keep that is BA at 2 volt, then voltage at B is equal to 4 volt. So, the voltage across the potentiometer becomes 2 volt. So, that means if I keep this one at 2 volt and this is at 4 volt, then I know that when potentiometer is varied, voltage at this point will vary by 2 volt, voltage at this point varies by 2 volt. If voltage at this point varies by 2 volt, then this also got to vary 2 volt by 2 volt, because this and this are always following each other. So, if this is at 2 volt, we know that this is at 2 volt. If this goes and reaches B, then this will go to this plus terminal, plus input will go to 4 volt, and automatically D also have to go to 4 volt. So, that means the expected change at D will be again 2 volt, because C is changing by 2 volt. So, D also expected to change 2 volt. So, next this the expected change at the expected change at that is change at D, expected change at D equal to 2 volt, that is equal to change at C, that is potentiometer change. So, if D you have to change by 2 volt, then if I take R1 R2 are equal, if R1 equal to R2, if R1 is nearly equal to R2, then to get 2 volt change, to get 2 volt change, to get 2 volt change, to get 2 volt change here, if these two are equal, we know that this point I have to change 4 volt, because if 4 volt change occurs here, you will get half the change occurs here. So, we need to get 4 volt change here. Now, the 4 volt change to take place means here it has changed by 4.6. So, we have 8 volt supply. So, 4 volt change is always possible. So, we can keep 2 volt change across this, because if I keep too much change, for example, if I take 4 volt change, if I drop 4 volt across this, then here I have to here change will be 4 volt, and here it will change 4 volt, then here it change you need a change of 8 volt at this point, that is 8 volt change across this, that is not possible. So, our assumption of 2 volt change that is required here is perfectly alright, because that will able to change 4 volt here, and that is what required. So, what actually can be now done is, since this is 5 volt Zener we have taken 5 volt Zener, if I make R1 R2 equal, then I will get 2.5. So, instead of that means 4 milliampere we need almost about 1 milliampere current, almost negligible current. I can make sure that this is also when at A also I can keep it say 2.5 volt. So, if I keep A at 2.5, so what I do is now readjust this. So, keep A at 2.5 volt, then R1 can be kept equal to R2. Of course, this will call for of course, I can keep B at 4.5 volt, that is makes potentiometer voltage becomes 2 volt then. voltage equal to 2 volt. So, 2 volt anyway will call for 4 volt change at the output, that can be easily achieved. So, I keep R1 R2 equal. So, I make it say to make the current small, I keep this one 100k or 470k. For example, I can keep R1 equal to R2 equal to 470k. So, if I draw the circuit now, that current transfer part, it looks like this. You have this, then I have this potentiometer, then this point is kept at 2.5, then this is 5k. So, this automatically I have to keep it 4.5k, that I can select these resistance. I can select this resistance. Then we have put this one to plus, then we had minus. The minus actually one end is we had two resistance. This is given to 5 volt reference. You had this resistance connect to this, other resistance here, and then so I put, we said we take 470k. So this and this we take 470k. So normally this is 5 and this will come to 2.5. So when it is at this end, then almost no current flows. We will see how to tackle that small differences. We will give 0 and span adjustment to take care of these small changes. So I can do this, and this is connected to this. Now only thing that is to be designed is this resistance value R or Rx. What is the value that I had select for Rx? Because we know when roughly about 17 milliampere current is flowing, we need to develop about 4 volt. So we will develop 4 volt. So we need required voltage is 4 volt. So required voltage across Rx is 4 volt at 17 milliampere current. At 70 milliampere current, and of course required voltage across Rx equal to almost 0 volt or very small voltage equal to 0 volt at about 1 milliampere current. Say it can be very small, that I can adjust nearly equal to 0 volt at 1 milliampere or less. Now this small voltage can be taken care easily, that I will show you a little later. So all that I need to concentrate at this point is that how much resistance I have to put to produce a 17 volt for say 17 milliampere, 4 volt at 17 milliampere. So the Rx into 17 milliampere supposed to give me roughly 4 volt. So that you can find Rx very easily by taking this. That actually, if we take this 34, you will have 6 3 90. So you will get about 2 for 35 ohms. So that is the approximately the resistance that is required for Rx. So if I put this Rx here around 235 ohms, then more or less the circuit design okay, but it is not perfect, because we said when 1 milliampere is flowing, this will produce 235 millivolt. That may not exactly match, because this is giving the voltage at this point is 5. Voltage at this point is 5, and if this kept at 2.5, at 5 will come 2.5 here. At that time, if 1 milliampere goes, then you will have 235 millivolt, half of that will come here. But then that fractions may not match exactly to make 4 milliampere. So what we normally done is, we will, to take care of these fractions, we will have adjustment, 0 and span adjustment is provided. So, what we do is now the current transmitter circuit can be modified like this. So, we take this, then we put on potentiometer here, that is connected here. We call this is a span potentiometer. This can be 235 or even it can be a little higher. So, it may be 250 ohms or so we can be connected. That extra thing can be taken care by this potentiometer. So, this is your 8 volt line, that regulated voltage. So, you will have potentiometer and then ground here, and then we have this that can be connected to plus, and the minus voltage is coming here, that actually you will have this is there. Now, one thing can be done, we can connect this one to 5 volt, then we can also have a provision to vary this voltage, or even we can vary this resistance little bit as a 0 variation. For example, I can have this variation, this resistance can be varied. I redraw this, I have everything on. So, I redraw this. So, what I do, I have this. So, that is the 0 part, and that is connected to 5 volt. So, this is kept same, R1, R2 are same, and then this is the potentiometer that is connected to this A. This we call 0 pot. So, normally what is done is the the potentiometer, that is this potentiometer is kept at one end, then they adjust 0 to get totally 4 milliampere here, then they move the potentiometer to this end, then adjust the span part to get 20 milliampere in the volt system, that is this current plus all other current put together, it becomes 20 milliampere. So, then again you come back to this end, adjust this to get 0, then go back to the other end, adjust this to get 20 milliampere. The span and 0 adjustment is provided to make sure that at other end exactly current 20 milliampere, at one end it becomes exactly 4 milliampere. So, this is how 420 milliampere current transmitter is designed, and then this is used as a current transmitter. Now, if you look at the entire circuit in one go, that looks like this, that is you have a supply say 24 volt, then we have our sensing resistance in the air, then the first input part will be a voltage regulator. So, that is done like this, then this resistance is used, then we have a voltage regulator, so this gives you 5 volt, then output is sensed partly, then we use the zener to boost the voltage which I already discussed, then we put the one small capacitor to avoid the oscillations, then we have our current transmitter connected here. Here you put span pot, then you have minus plus, here our potentiometer is connected and our 0 pot is connected here. So, you connect this to ground, then the potentiometer end connected to plus input, then we will have these two resistors are connected here. and this goes to 5 volt supply, 5 volt reference. That is the complete circuit diagram of the 4 to 20 milliampere current transmitter. So, what we have done is we have actually we have a voltage regulator part here, voltage regulator part. So, that makes sure that voltage across this is constant. Then when mechanical system moves, voltage at this point varies. If it increases, the voltage increases, then we know that if the voltage goes up, this voltage also have to go up. Now, if this is not going up, if this alone increases, then this will be less and this will be more. So, output will go high and the current will increase through this. The current increases, this voltage will increase and automatically this also will increase. So, that if this increases, this also increases. So, that way as long as I move this, this also will correspondingly follow this voltage. If this voltage increases, this also will follow this, that is minus input will follow the plus input by increasing the current through this. Because if the current is not increasing, then this voltage will be less compared to this. Then automatically since this is high, output will go high and more current will go. In case if the current goes very high, then this voltage will increase and this voltage will go up. If this voltage goes higher than this, that is inverting input goes higher than the non-inverting input, then output will come down, then the current also will come down. This way the current through this is controlled by the fact that this voltage has to be equal to this voltage. By this fact the current is continuously regulated, and the current that is flowing through this depends only upon the position of this. This current of course is same as this current, because the current flowing through this plus current flowing through this, which is constant, then some current is flowing here, that is also constant, some current is flowing here, that is also constant. Since all the other current are constant and this is the only variable, so once you vary this current changes. So, one can adjust the 4 and 20 milliampere by adjusting this 0 part. For example, this is 0 part, this is a span part. One can adjust the 0 part to get 4 milliampere when the potentiometer is at one end, and when the potentiometer at the other end, you can adjust the span part to get 20 milliampere. By repeatedly adjusting 0 and span a few times, one can make this 420 milliampere current transmitter for the potentiometer. Now, if you recollect our earlier discussion that the current flowing through this, so it only depend upon this potentiometer variation. It should not depend upon this supply variation or this load changes, because up to 600 ohm they may put this. So, for example, if I put 600 ohm or 100 ohm, then whatever current is there, that should remain constant. For example, if I suddenly remove this 600 ohm, put 100 ohm, then also same current should flow, because that is that will be definitely assured, because we are keeping here only 8 volt and this is 24 volt. Even if this voltage say goes to 22 volt, and even if 20 milliampere current, which is maximum, this will develop 12 volt only. So, out of 22 volt, 12 volt are gone across this. So, you have 10 volt left. So, 10 volt we are leaving 2 volt for this, and we are getting only regulating only 8 volt. So, only if the voltage goes less than 22 volt or the resistance goes more than 600 ohm only, the output will not be maintained 8 volt. Once output is not maintained 8 volt, then if this decreases, then this also will decrease and current also will decrease, and the 420 milliampere current will not be valid and it will not be maintained. So, so as long as this is not going below 22 volt, it is okay. Similarly, if I put 100 ohm, there is no problem, because 100 ohm will create only 100 into 20 milliampere will give only 0.2 volt. So, 22 minus 0.2, that you will get almost 21 volt here, and that easily gives 8 volt. So, even if you short also, you will get same 20 milliampere only flowing, that current will not get affected. So, current will not get affected because of this change or because of this change. Then all the other currents are actually kept constant. So, they are not going to change. So, current will remain constant. Then other discussion is what happened to the noise pickup. Suppose if this is we set this loop area is long, normally we keep this is about a kilometer long, then the change in magnetic field will reduce the voltage, that should not create a problem. So, that what happens is that voltage I represent like this, because that will be in series with this, that is actually B A n omega cos theta, where B is the external magnetic field, area is the area of the loop is this, A is the area of the loop, and in this case n is 1, number of turns, that n is 1. So, I remove that. Omega is the frequency of the applied magnetic field, cos theta is the angle of orientation between the field and the loop. For normal purpose I keep that as 1. So, induced voltage is actually this, that voltage comes in series with the applied 24 volt. If it comes in series with the applied 24 volt, then actually what really happens is the circuit, that is this voltage regulator, really receives not this 24 volt, that is supply voltage plus or minus this AC voltage is what is coming. Suppose even if the picked up voltage due to the magnetic field is 1 volt, that is 1 volt AC, say 50 hertz, then you have 24 volt plus or minus 1 volt what is appearing here. But nevertheless, the voltage change at this point, will not change the output voltage, because the frequency response of this operational amplifier is more than 50 hertz, is much higher. So, as long as the noise frequency is much lower than the frequency response of this operational amplifier, whatever change that is coming here, if this increases, then this voltage will increase and this will increase, automatically this voltage will decrease and this decrease and this will decrease. So, even if you have a 50 hertz AC, all that it is doing is this dynamically adjust that 50 hertz field, and you will get only 8 volt here, and no AC component will be present here, because any small increase in voltage at this point due to the noise that is present here will increase this, and automatically that will pull it back. So, since this is faster than 50 hertz, and it is essential to remove the noise, that is the frequency response of this loop, this loop should be much higher than the noise pickup. Then the noise pickup, the output voltage, this 8 volt will not have any AC component, and this 8 volt will remain constant. So, the noise voltage will not create any problem in the circuit, because if there is no noise voltage here, this is correct and this is correct. Of course, you may have noise voltage induced this part of the loop, for example here. Now, this also have to drive the current like this only, but then we know that this, as long as this voltage is not changing, this current also will not be changing. So, external noise will have no effect on the current. That is why this current transmitter is used, and also only 2 wires are used. So, in practical usage we find that there is no problem because of the noise, and we need not put too many wires, because the wires have to be long. So, too many wires will cost more money, and so that problem also solved, and then noise pickup is not there, and even the small change in the voltage of this and even load change or the wire resistance change also will have no effect on the signal here. That is how these 420 milliampere current transmitters are made, and it is used in the industry. So, with this I will stop this lecture. So, next class we will see how to make error budget for this circuit. Thank you.